Hello everyone, we continue again in chapter 17 to discuss 17.2 second derivative and the nature of stationary points. Okay, let's see what is our learning outcome for today's session. You will be able to use the second derivative to determine the stationary point's nature and apply the second derivative to solve stationary problems. Let's start with recalling of what we have in the previous session. You've learned how to determine the nature of stationary point using first derivative. But not every nature can be determined simply by just using first derivative. So, let us learn how to determine the nature using second derivative so we have option and we can confirm the nature of the stationary point. So let's see the diagram below that is showing you the curve of y equal x plus 4 over x minus 2. We can see that it has one stationary point and the point L is a minimum point. If we want to find out dy dx, can you derivate x plus 4 over x minus 2? So this is the result. The curve gradient function become 1 minus 4 over x squared. And let's sketch this graph and we obtain this curve. For this curve, we can observe that through x equals 2, dy dx increases as x increases. And we can say that the rate of change of dy dx is positive at x equals 2. Or later, we can use the symbol of the second derivative is positive at x equals 2. If we derivate 1 minus 4 over x squared one more time, we will have the function become 8 over x cubed. Let's see at x equals 2, if we substitute it to the value of x in here, we have 8 over 2 cubed will be equals 1. And this is greater than 0. So, as we observe, the second derivative will be positive. And for that, we can conclude that the stationary point L 2, 2 at which dy dx equals 0 and the second derivative is positive will be a minimum point. Let's continue with this second diagram, which is showing you the curve of y equal 3x minus x cubed. As you know, this is an up-and-down parabola with a stationary point of maximum h 1, 2. Let's do it again to have dy dx of 3x minus x cubed. dy dx become 3 minus 3x squared. Let's see the graph of this dy dx over x. In here, we can see that dy dx will be decreases through x equals 1. Or we can say that the rate of change of dy dx is negative at x equals 1, or the second derivative of y with respect to x less than 0 at x equals 1. So we can conclude in here using calculation. If we have the derivative of 3 minus 3x squared, we have the function become minus 6x. And if we substitute x equals 1 at the stationary point, minus 6 times 1 equals minus 6, and it is less than 0 as observed. So we can conclude that the stationary point h 1, 2 at which the dy dx equals 0 and the second derivative is negative will be what kind of nature? This is a maximum point. Next, let's see example 1. Find the coordinates of the turning point on the quadratic curve y equal 8x minus 23 minus 3x squared for 1 less than equals x, x less than equals 5, and sketch the curve. So in here, dy dx become 18 minus 6x. And we will find out the stationary point with making dy dx equals 0. And we have x equals 3. Now we calculate the value of y and we substitute it here. Y equals 18 times 3 minus 23 minus 3 times 3 squared. And we got y equals 4. So the turning point is 3,4. Now let's continue to find out the nature of the stationary point. The second derivative of the function is minus 6. And since it is less than 0 at x equals 3, hence the turning point 3,4 is a maximum point. The sketch of the curve is shown below. It is a parabola that is up and down with one stationary point of maximum at 3,4. So this is the graph of y equal 18x minus 23 minus 3x squared. Conclusion: in this lesson, you already know that we also can use the second derivative to determine stationary point's nature. How to find it out? First, you will have a maximum when dy dx equals 0 and the second derivative is negative. You will find out the nature, which is minimum, when dy dx equals 0 and the second derivative is positive. That's all for today. Let's continue again later in the next meeting. See you again soon and God bless you all. Bye bye.